This video gives an overview of the main strap options and features. We start with the main menu, which gives a list of all the models designed in the current folder. The program comes with complete file management. We can copy, delete, zip models. We'll now move to the geometry of one of the models in the list. The model consists of elements joined at nodes. The main options are node definition, restraint or support definition, beams, plate elements, springs, solid elements, wall elements. For example, in nodes we can define single node, line of nodes, grid of nodes by equations. We can choose a cylindrical coordinate system, and we can unify nodes at the same location. Restraints can be fixed, pinned, or various combinations, and can be rotated. There is a rigid link option to connect selected nodes. In the beam option, we can define single beams, a line or grid of beams, a bracing system. We can offset beam ends from their end nodes. Releases can be defined to create pinned members. In the properties option, we can define by section properties, select from a steel table, define various sections by dimensions, or built up steel sections. Elements are triangular, quadrilateral. There are options to define a grid, a surface, or a mesh of elements. And the properties are the thickness, the material, and they can be isotropic. Spring elements can be in any degree of freedom. They can be unidirectional, and they can be nonlinear, and there are also gap elements. Solid elements are defined by selecting nodes, or they can be lifted up or rotated from a plane mesh. Wall elements consist of a series of segments which can have openings. Various construction stages can be defined, each with different loading, and the program collates the results from all stages. Submodels can be defined. These are repetitive sections of the model which are defined only once, then added at multiple locations. Here we have 6 submodels. The advantage is that they are defined only once, they are solved only once, only have to be revised once. We will now move on to load definition. Loads can consist of multiple loading cases and combinations. Each load case can consist of joint loads, beam loads, element loads, support displacements, and global loads. Joint loads can be applied at any degree of freedom. Beam loads can be uniform, linear, point loads, temperature, self-weight, pre-stress, lack of fit, or surface loads. Element loads can be uniform, linear, temperature, self-weight of walls, or a bilinear surface load. Support displacements can be defined for any degree of freedom. Global loads are loads defined at any coordinate on the model and not on specific elements, beams, or nodes. The load may be a point load, a line load, an area load, or a saved load pattern. The program searches for the adjacent nodes, beams, or elements and divides the global load to those nodes, beams, or elements. Load cases or combinations can be deactivated prior to solving the model. We can also define moving loads, chess pattern loads, calculate the p-delta effect, and we can define wind loads on selected panels, on the entire structure, on the roof, or on individual exposed elements. Combinations of load cases can be created here before the solution or after the solution. When all the loads have been created and checked, we move on to solving the model. After solving the model, we move on to the display of results. We can define combinations of the load cases at this stage. Results can be displayed graphically, or they can be displayed in tabular form. We'll start by displaying slab results on one of the submodels. We can draw contour maps of all the slab results, and we will first display the moments in the x direction for one of the combinations. The contour map values are shown in the table on the side of the screen. Similarly, we can display stresses, design moments, and the reinforcement at either face. We can also display the elastic deflections. Another option is to create sections through the model and display the results along the section line. Again, we will select bending moments. We can zoom in on any part of the model, and we see the bending moment diagrams for two sections previously created. For tabular results, again, we can select any result type and can sort the results by loads or by the elements. For moment results, the following table is displayed. The results are shown for each combination, and the maximum and minimum results are also displayed. Other options available are calculating the slab deflection based on the cracked section. Punching reinforcement can be calculated, and there are options for averaging results at locations of high moment concentration. Crack widths can also be calculated, and reinforcement to reduce crack widths can be designed. The first step in dynamic analysis is calculating the mode shapes and the natural frequency. We have to define the masses and weights acting on the structure, and we can do that manually, or we can define masses based on the self-weight and the static loads. After solving for the mode shapes, we move on to dynamic design. We can also display and animate the mode shapes. For example, we'll select mode shape number 5 and animate it. Now we'll move on to seismic design. We can select any one of many design codes and specify the seismic factors, including scaling. After doing the calculation, the resulting seismic load cases can be appended to the static results. We now continue to structural steel design. The program can either check a section or select a section. If we select a section, we can limit the selection to a section type. We can use the same type as defined in geometry, or we can create groups with several section types and limit the selection to the group. The program will always select the optimal section. In addition, we can say that a series of beams must have the identical section. Other parameters that we can define are intermediate supports. The supports are for major axis bending at either face or lateral buckling about either axis. We can also combine several strap members to form one design beam. After computing the sections, we can display detailed results. The detailed results show all the design data, the moment diagrams, the section classification, and each of the design checks: shear, moment deflection, axial, lateral torsional buckling, and combined stresses. The concrete module designs beams, columns, walls, and slabs. We can also generate drawings for all of the above. The program identifies automatically continuous beams. After setting the parameters and computing them, we can display the detailed results. As we can see, the program calculates required reinforcement areas, the links required, and calculates the deflections based on the cracked section. For columns, the program automatically calculates the additional moments for slendered columns and calculates columns with biaxial moments and arranges the reinforcement. The links or stirrups are also calculated. For walls, the program calculates, similar to columns, the reinforcement arrangement in every segment. For slabs, the program calculates the required reinforcement, top and bottom, in both directions, and arranges a drawing. Similarly, for walls, the program combines the reinforcement in all the segments.